Okay, this video is for Chapter 10, Section 2. It's all about trapezoids, kites, and rhombi. We're going to be looking at the area of these figures. Let's get started. First, we're going to start off with trapezoids. We've got to remind ourselves the parts of the trapezoids. Trapezoid has two parallel sides, and the other sides are non-parallel. We have base 1 here and base 2. We have a leg here and the other leg. And we have a height. Now, we have one little piece missing of the probably dotted line of the right angle here. The base and the height are perpendicular. The height is not a side of a trapezoid. Rather, it is the perpendicular distance between the two bases. Also, this one looks like it's an isosceles trapezoid, but it's not. It's just a regular trapezoid. Base 1, base 2, two legs, and a height between the bases. Okay, so the parallel sides are the bases, the non-parallel sides are the legs, and the height, hopefully we can see this, is the perpendicular distance between the bases. That's what the height is. Now let's look at the area of a trapezoid. So first of all, here's another trapezoid. Probably can be seen a little better. What we're going to do is, we're going to copy the trapezoid, flip it over, and attach it to the matching side. And there we go. Now, all of a sudden, the two trapezoids come together to form one giant parallelogram. And we just learned the other day that the area of a parallelogram is base times height. So, our area for this trapezoid, remember we want to find the area of just one, is 1/2 the base times the height. But we have to make a note. The base is actually base 1 plus base 2. This whole base times the height. So B1 plus B2 times H. Plug that into the formula, and what we ended up doing is just moving the height to the front. So instead of 1/2 base times height, it's 1/2 height times base. 1/2 H times B1 plus B2, and that is the derivation, or where the area formula for a trapezoid comes from. So let's see how we would use this in a few examples. So here we go. Let's look at example number 1. Now this is a trapezoid, and it's given us everything we need. So we have area equals 1/2 height times B1 plus B2. Now we just need to plug in what we know. The height is 7, base 1 is 11, and base 2 is 5. This becomes 1/2 of 7 times 16. Half of 16 is 8, and 8 times 7 is 56. So we have 56 centimeters squared. That's the yellow example number 1. Now we look at example number 2. The area equals 1/2 height times B1 plus B2. Plug in what we know. 1/2, I don't know the height. It doesn't say. And that 5 is not the height. But I do have a 4 down here, so I'll call that B1. And I don't really have a B2, except for that I do know that this is isosceles, so if that's 3, there's probably a 3 over here as well. And this is 4, so there's a 4 right there. So now my base is 3 plus 4 plus 3, so 10. I also need to find the height. Well, what do we do when we need to find a missing side? The Pythagorean theorem. So make sure we look here. Here's a right triangle, 3, 5. Looks like it's going to be a 3, 4, 5 right triangle. But if we had to, 3 squared plus 4 squared plus b squared equals 5 squared. 9 plus b squared equals 25. B squared equals 16, and b equals 4. So we now have our height, 4. So I have 1/2 of 4 times 14 Half of 4 is 2. 2 times 14 is going to be 28 meters squared. So there's our second example using the Pythagorean theorem to find the missing part. Now our third and final example. This one we write down, again, same thing. 1/2 height times b1 plus b2. I like to write the formula every time. Helps me start to memorize it. So 1/2 the height, which is going to be, I don't know yet. Base 1, 18. Base 2, not sure yet. So we're going to have to find this information. Okay, well, here's a 30, 60, 90 right triangle. We could use special right triangles. 12 feet is the hypotenuse. In a 30, 60, 90 right triangle, that means that the base or the short leg of this triangle is 6. And that means that our long leg is going to be 6 rad 3. So, now I know what the height of my trapezoid is. It's 6 radical 3. And I also know what the top base is, because if I take 18 minus 6, I get 12 for up here. So my other base is 12. We should probably put that in the picture so that we don't forget. There's our 12. Okay, but we have enough information here. We can now say 1/2, 6 radical 3 times 30. 1/2 of 6 is 3. 3 times 30 is 90. So 90 radical 3 feet squared. There's our third example. We now move over and look at rhombi and kites. Okay, let's take a look at kites and rhombi. Turns out they're going to have the exact same formula, and we don't even have to use the formula if we just want to sort of understand the idea. Here's a kite, and in this kite there are 4 triangles. And technically right now we know how to find the area of a triangle, so if we wanted to, we could just find the area of all 4 triangles and we could go ahead and find the area of this kite. For example, I could say that the top triangle is 1/2 a base of 10 and a height of 2. And that would be 1/2 of 20, which is just 10. And the other triangle, the one below it, would be 1/2, its base is also 10, but its height is 8. Half of 80 is 40. So it looks like the area of this kite is going to be 50, because we have that triangle 1/2 10 times 2, and this triangle 1/2 10 times 8. Now, it turns out, however, that we can turn a kite into a rectangle and help us understand what the area of the kite is from a formula standpoint. So now at this point you should have the kite drawn, because I'm going to erase parts of it and draw it somewhere else. I'm going to take this part of the kite off, and I'm going to flip this triangle over and put it right here, in which there's the 8 and there's the 5. Nice little rectangle there. And I'm also going to take this triangle off and put it here. Now, when I do this, we have taken the parts of the kite, flipped it around, and made it into a nice rectangle. The area of this rectangle is base times height, 5 times 10. Now, that's kind of interesting because 5 represents 1/2 of what used to be this diagonal. 5, 5, half of that. And then this diagonal is the full 10 still. So what ends up happening is the area formula is 1/2 of diagonal number 1 times diagonal number 2. I take 1/2 of 10 which is 5, and I take the other 10. So the diagonals in this case were 1/2, 10 times 10. 1/2 of 100 is 50, which is what we got by adding those parts up. Now I guess we could look at the rhombus and see if the same thing works. In this rhombus, we can say, okay, how do I find the area of the rhombus? Maybe I just find the area of all 4 triangles. Well, a triangle is just 1/2 base times height. And this triangle has a base of 3. Uh-oh, we don't know the height. But wait, it's the same Pythagorean theorem as earlier. 3, 4, 5. Okay, so this triangle is 1/2, 3 times 4, which is half of 12, which is 6. And there are 4 of those triangles, 24. Well, now that we know that's the area of the rhombus, I wonder, is there another way we can see this? Again, take the triangle off and put it here. So here's a 5, and here's the 3 and 4. And take that triangle off and put it here. Here's a 4, because this is a 4, and that's a 3, and there's your 5. Now if I erase this, I'll leave the 3 sticking out there. Notice it is turned into a rectangle. And this rectangle's area would be 1/2 or 3 base times height of 8. 3 times 8. Well, what I'm noticing is that 3 is half of what that diagonal used to be. That diagonal used to be 6. So if I did 1/2 of 6 times 8, I would get 3 times 8, which would give me 24. The answer. So it looks like this formula held true again. Go back to the original rhombus, and now we can say that the area of a rhombus is 1/2 diagonal 1 times diagonal 2. 1/2 diagonal 1, which is 6, times diagonal 2, which is 8. 3 times 8 is 24 units squared. So there's your area of a kite and rhombus formula, and that's it for video lesson number 2 about chapter 10, section 2.